Very excited to invite StructureCraft. Lucas Ebb is going to join us and talk about computational design, the use of computational computing for mass timber. Lucas has presented with CanBIM before in the past, I believe. Hopefully, I think last year, right? And he's got 50 years working in the industry. StructureCraft does amazing projects all over the world. Complex form design, one of the leaders in this industry, certainly. And excited to have you join us and share some of your knowledge.
Yeah, thanks, Thomas. It's great to be here. So let me just share my screen and we'll get started. So yeah, I'm going to talk a little bit about computational approach to mass timber and using some examples of some projects we've been completing recently. And really just, I guess, talking about potentially a different way of thinking about putting BIM into your designs and moving past the M in BIM, past the modeling, and through to kind of applying a computational approach to design thinking. So StructureCraft, we're a team of structural engineers and builders based out of Vancouver, but we work kind of across North America and also do a decent amount of work in China, some of which I'll show you today. And our team is kind of interesting because we're kind of a vertically integrated team. So we've got structural engineers and we've got computational designers, project managers, and manufacturing and installation capabilities. So for the timber component of the structures, we take an end-to-end approach. And we also act as the structural engineer of record on the projects we're involved with. So we're working directly with the architects and the owners to kind of come up with the overall structural concept of these buildings. And our history as a company founded about 22, 23 years ago is founded in this concept of a master builder, the idea that structural engineering is not just about figuring out how to make the components work from a structural standpoint, but also how do you build, how do you manufacture the buildings you're actually ideating and creating with the architects. And so the company is founded by my father, and he did a lot of work with an architect named Bing Tom. This is one of the first, I think, timber space trusses of its type here just outside of Vancouver. And then he went on to do some really neat projects. This is downtown Washington, D.C., a big theater project using an all timber backed facade. And then moving on to projects like the Speed Skating Oval for the Olympics here in Richmond, which was a huge, almost 100-meter clear span timber roof, a real showcase for what timber can do. And so I wanted to talk briefly about this concept of what a master builder is. Pre-1900s, guys like Eiffel and Brunel were these master builders who kind of functioned as both engineer and builder. And sometimes architect as well. And then through the Industrial Revolution, we saw the segregation of design into different components. And now we have mechanical engineers, structural engineers, architects, civil, geotechnical, and then we have on the construction side and on the trade side, a lot of incredible amount of segregation. So we moved away from this point of having people who take more responsibility towards more of a point of segregation as a typical approach in the industry. This design to build approach. And Le Corbusier, put it interestingly, and he separated the engineers and architects' responsibilities into these statements here. And so I'm going to talk today a little bit about applying this computational design approach, actually starting with more complex structures. We call them freeforms. And actually, funnily, it's actually more easy to implement a computational approach on freeform structures than it maybe is on the mass timber structures. And I'm going to start with the smallest little canopy. This is the little forest canopy, and it's using this concept of we had a whole bunch of leftover glulam from a project in China, and we're trying to use these glulams leaning at different angles, but all the same lengths or similar lengths to create this canopy for a client over there in China. And so we kind of are using these genetic algorithms and these kind of optimization approaches to satisfy a whole bunch of different constraints. And that's sometimes what we mean when we talk computational design is putting constraints or pre-programmed constraints into our design. So here, we're saying that the columns can't hit each other and they have to miss each other at the roof, and then they've got to be a certain size. They've got a max length of 7.5 meters because that's what we have. And then we're using nail laminated timber because this is built in China where there is no CLT. And so the weak axis cantilever capacity of NLT is a problem. So we put constraints on that. And then we say that all the columns must have a no net positive lean. You don't want the structure to fall over under its self weight. And then so you put all these constraints in place. And what happens once you do that is you're left with kind of this optimization technique, which kind of allows you, oops, sorry, I skipped ahead too far here, but it allows you to kind of explore what we call the solution space. So this is kind of like an optimization algorithm running and conducting the structural analysis at each stage of the form finding of this tiny little structure. And this type of approach can be used on much larger structures to optimize both structural performance at the same time as other constraints. And so this is the finished canopy here. So a really small structure, but kind of an interesting example of using computational approach to building and designing these mass timber structures. And so the question, I guess, for us is, as we move from a smaller structure to larger structures, how do we use those same approaches in some of these bigger structures? And so the next project I'm going to show you is in Taiyuan, not too far away from that little canopy I just showed you. And it's a project with the Lubin Meisel architects for 3 giant kind of timber grid shells. And these are biodomes. So inside each of these 3 grid shells is a different set of flora and a different environment. One is an aquatic dome, one is a dome for housing desert plants. And so each of these 3 domes have a different internal environment. And the architecture was inspired by this kind of idea of a clamshell. And here you see the kind of grid of the structure coming through, and how the 3 different shells kind of have 3 different, very, very different feels when you go inside. One is the largest one is a clear span of about 90 meters or almost 300 feet. And the smallest one is maybe almost a third of that size. So much different scales and different structural problems. So that was quite an interesting challenge. And so to kind of create these types of structures requires a completely computational approach. And so our company kind of over the last 5-10 years has gone through this phase of developing a computational approach primarily for these higher end, kind of more complex structures. But as I'll show you towards the end of this presentation is taking that same computational approach, which we kind of say develop first on the higher end projects, is quite interesting when you start to apply it on the more traditional mass timber structures. And so here you start to see some of the approaches that we're using on this particular set of grid shells. We're using this concept of a geometry concept called a geodesic, which is basically the shortest path between 2 points on any freeform surface. And then we're investigating parametrically the actual density of the grid shell, and there's a whole bunch of constraints around the density of the grid shell, including the fact that these domes are covered in glass. So this is all AA and some singly curved glass. And here we're running an optimization using k-means clustering to basically try to cluster the different shapes of the glass panels. But each of these glulam elements, which kind of comprise this bidirectional grid shell, some of them are doubly curved. And so what we're doing here is we're taking a singly curved billet of glulam, and we're actually milling that singly curved glulam into a double curvature. And you can see all the pre-drills for the screws, etc., already done in the factory. And so there's this prefabricated unit panel of a grid shell, and then you can kind of get the sense for how large these structures are. This is the largest of the 3 domes. And so, actually analyzing and designing a structure like this requires a complete computational approach. You can't go and do your traditional structural analysis and design approach where you kind of have this iteration of one form from the architect, another set of analysis. You have to have a fully integrated parametric workflow. And so here you can see us kind of analyzing the structure in real time there with the different wind directions. One of the biggest challenges for the largest grid shell is actually how do you tension this cable net that we had under the largest dome. And so these are sketches of ideas of how do we create this kind of casting, which connects a diagrid of cables underneath up to the timber grid shell on top. And these castings that we developed are really interesting because they actually are rotationally decoupled components, which allow each cable to kind of cross at different angles as they cross underneath a node, and then yet be clamped in with these kind of epoxy holes so that the cables are locked to create shear stiffness between the cable system underneath and the grid shell above. And then the step you just saw there, where the grid shells, I'll just rewind to that, where the castings are getting pulled closer to the grid shell above, actually induces tension into the entire cable net, so it lengthens all the cables. And so, once you come up with these ideas and these concepts of these castings, then you want to put them in place across the whole grid shell, I mean, you have to use a computational and a design approach. Yeah, you got to use Grasshopper, you got to use C# coding, you got to use all that type of stuff. And so that's been a real driver for us in terms of creating these structures, is kind of having to create these computational approaches for these larger scale freeform structures. This is some of the structural testing we did for the project out at our manufacturing facility just outside of Vancouver. But all the way through to this computational approach has got to also go through to the shop drawing phase and the CNC file generation. So here's there's thousands of different unique glulam components in the structure, including paneled shop drawings. All of these are generated from inside Rhino using some custom C# code that we're in this branch platform that we're creating internally to actually automate the creation of the shop drawings, the creation even of the CNC files. And so we're working with, in this case, 2 different glulam manufacturers in Europe, two different plants, and we're giving them the CNC files so they actually just program it directly from our BTLX files rather than having to do their own CAM processes in-house. And there you just saw the container packing. So we're having to figure out how to efficiently, it's kind of like a 3D bin packing exercise. How do you efficiently pack all these different unique elements into shipping containers? On the installation side, you can see we're kind of creating these lines of prefabricated panels and then infill strips in between, which gives us the ability to actually control install tolerance. This is on site in China. We had several engineers and obviously site supervisors controlling the whole installation, but this installation process is going 24/7 in China. It's a totally different speed of construction to what we're used to here in North America. And so there's hundreds of workers working all day and all night, and you can only control so much. And so you have to have rigid quality control procedures in place and documentation of the actual construction process. And that the projects like this actually really forced us to go digital, because we had to be able to see all the quality control information as we're building it. Me and our lead engineers are based here in Vancouver, and our guys in China are having to be able to communicate through these digital platforms. We're using Procore, for example, to be able to confirm the quality and the installation of all the screws and et cetera, so that we can get happy with the actual structure. So these freeform structures have really been a driver for us in enforcing a computational approach. And then we're actually kind of using some of these techniques that we've developed here to now look at the mass timber structures, which are obviously, there's many more of, and they're much, 85, 90, 95% of our building stock is the more traditional type of structures. But inside you see here kind of this really neat 2-layer doubly curved grid shell. It's not even a sphere, actually. It's kind of like almost an ellipsoid, the geometry of these domes. So really a tribute to what's achievable with timber, and starting to show that timber on a freeform scale can achieve just the same as what steel can achieve, which I think architects are more and more starting to realize is really the case, which is really exciting. And here in North America and the US and Canada, we're starting to see a lot more interest in what we can actually do with timber, not just for mass timber, for the prototypical 7, 8, 9, 10-story buildings, office or residential, but for higher end structures. Now I'm going to show you kind of a final project in China, which is just under construction right now, where we took the technology that we developed for those domes and we kind of took it to the next level. This is a series of barrel vaults in Tianfu in China, and this is about, I guess it's about 75,000 square meters roof area. So it's about 800,000 square feet of mass timber. I guess you could call it mass timber. Timber vault structures. They're basically arches. And so that makes it, I think, the largest timber structure in all of Asia, and certainly one of the largest in the world at 800,000 square feet. And these 5 vaults, clear spanning up to the biggest clear span for this vault here is about 115 meters. So it's pushing well over 400 feet clear span. And the challenge the architect out of Beijing posed to us as we were involved in the concept of development for the structure back 2-3 years ago was, can we find a way to expose the glulam on the outside of these vaults so that people can actually see the wood? And so that's a real challenge from a durability perspective. Can you really expose the wood. And you can see the architectural concept was actually keeping the cladding on the inside. And we ended up cladding the bottom chords of these trusses, but the top chords are actually exposed, which is really neat. A really neat architectural kind of statement as you walk up to these giant vaults. And so here you can see what these are. They're basically covering buildings. So they're actually open-ended barrel vaults. And they're really just acting as an environmental cover for other structures and buildings underneath museums and exhibits. It's a giant greenhouse exhibition, these series of vaults. And so this is our kind of initial structural concept, this idea of trusses, which triangular trusses, which kind of expand from the foundations and kind of neck down to the peak of the arch, and then expand back down again to the foundations on the other side. And so again, you know, obviously having a computational approach in Rhino and Grasshopper for a project like this is critical. And so you can see each of these trusses are almost individual. So from a seismic and lateral standpoint, we're looking at these trusses as being able to cantilever off the foundations by themselves. And so in the early days, we're looking at structurally, you know, do we look at a 2-pin arch, or do we look at an arch which is actually fixed into the base? And here you can see the moment diagrams for each of these different types of arch typologies from a structural concept, or do we look at a 3-pin arch where we actually put a pin up at the apex? And so, you know, the initial concept was using X cable bracing, but then we actually came up with a concept to change it to this kind of splayed V bracing system, which is really interesting, and actually created this idea, which the architects were really interested in, of this ephemeral connection between the top chords of the truss and the bottom chords. You almost can't see them. These are just very thin steel plates. So it almost looks like the truss isn't a truss at all. And so that was a key structural concept. And then figuring out how to break these trusses down into prefabricatable components, which can be prefabricated into smaller units in a shop and then shipped to the job site. So here you get a sense of the scale of the project, and this is our 3D model showing the kind of trusses clear spanning across these spaces. And this is during construction sequencing, and how do we build this, and in what order do we build this was a real challenge, because you got so much other construction works happening underneath these vaults. And here you can see every single one of these arches arranged in order of their span, and you can see the different shapes and geometries that we actually had to design for, which is quite complex. And so a lot of questions around, should we use a catenary type shape versus elliptical shape, and the actual shape and constraints of the geometry was an interesting challenge in and of itself. So here you get a sense of the scale. Here's one of these big prefabricated pieces I was showing in the 3D model getting lifted into place on site, and you start to get an idea of the scale of these giant trusses. And literally just about 3 or 4 weeks ago, the last truss was lifted into place on site in China. And here you can see the cladding is in progress on the site. And so this is a real tribute, I think, to what's achievable from a long span perspective with timber. And again, this computational approach to, you know, making every single shop drawing, making every single 3D piece, and driving the CNC files. This is something like 6,000 or 8,000 cubic meters of timber in these structures, right? So a huge amount of wood, many different manufacturers, I think 3 or 4 different glue manufacturing plants involved at the end, and all having to sing from the same songbook, and all having to be driven by that same 3D model, which we controlled. So a really neat structure, and I'm excited to see this opening in the next 3 or 4 months here. And moving back to stay on the freeform subject, but moving back to the US, there's a structure we recently completed for the University of Idaho, the basketball arena. And Opsis Architecture out of Portland, their concept was to kind of follow the Palouse Hills, these rolling hills of the surrounding area, and create this doubly curved roof, which kind of took off of that concept. And so the question for us was, can we, from a cost standpoint, can we cost effectively create a doubly curved timber roof? The University of Idaho had a very tight budget, you know, in the 30 million range, $35 million range for this entire structure. And so right at the structural concept stage, we started working with Opsis to kind of try to figure out what structural techniques can we use to really minimize the the weight of the structure, minimize the cost of the structure, and come up with something that's buildable, but still achieves this idea of double curvature. And so this is some of the kind of sketches of the different structural truss techniques we're using to reduce the size of the glulam's and achieve these clear spans. And we're using optimization techniques. So, once you have this idea of a king post truss with, struts and cables, we're able to start exploring the solution space of the geometry for these trusses and look at, what is an actual efficient structural geometry for these trusses. And you can kind of see that the last bit of this video here, you can see the glulams are sizing themselves at each step of this optimization. You can see how much smaller you can make your elements by applying these types of computational approaches. And there's a big giant span in the middle where we're kind of spanning these trusses over top of a practice gym and kind of allowing the practice gym to be connected to the main span. So this was a really interesting structural challenge, creating this basically portal frame, prop cantilever portal frame is what we ended up doing, which basically has these columns thrusting into these beams with a huge load, but a massive axial load thrusting from the column into the beam. And so looking at the structural connections required for that, and then test fitting these columns and beams in our shop. The column actually isn't in the same plane as the beam, so it's kind of leaning at an angle, making it fairly tricky on the manufacturing side. But for this portal frame, it's still applying this computational approach of how do we want the structure to behave. We control how we want the structure to behave and the forces in the structure by controlling the stiffness and the load pass. So a really neat kind of this proscenium arch, which all these king post trusses come and land on, allowing the extended seating in the back half of the arena to kind of connect to the front half of the basketball arena. And so here you can see this kind of doubly curved roof surface. And so we worked a lot on that surface to actually kind of rationalize the glulam and break it into, we're working with 2 different Idaho glulam manufacturers on this project, and they couldn't handle every single glulam beam being a different radius and a different geometry. So we had to, bin all of the beams and make sure that there was a lot of repetition of the different radii. This is just showing some of the different structural concepts we were looking at for this kind of proscenium arch, or this portal frame that kind of frames the seating in the back. And the geometry of this was really framed by this view corridor. We had to make sure that the people sitting in the farthest back of that seating could still actually go and see right down onto the arena itself. And now we've got this doubly curved surface. And so another question is on how do you clad it? And again, this is this idea of creating panels, groups of panels which are similar in geometry. So every color represents a similar geometrical panel. So we don't have to have, every single panel unique despite the double curvature, but we're able to have some repetition throughout the structure. This is opening actually in October. So this is basically complete, the structure. I don't have any finished photos yet, unfortunately, but this gives you an idea of what the inside of the structure will feel like. So yeah, that's a little bit about this computational approach on freeforms. And now I want to talk about mass timber. Mass timber is as a concept is much simpler from a structural perspective, but it has very many of the same challenges. In fact, sometimes more challenges than the freeform structures do, because the freeform structures, you have kind of one, let's say, concept, and you're kind of repeating it across a large space. And so you're able to spend a lot of time refining that one concept and creating let's say, a holistic optimization kind of set of criteria for your structure. But when you're dealing with more regular buildings, this is a project in Atlanta we finished a couple of years ago now. It's about 220,000 square foot building, mass timber building, and it looks so simple, right? It's a big rectangular box. But when you're dealing with more regular buildings, the actual number of unique boundary conditions is way more than when you're dealing with these freeform structures. You actually have a lot more different things going on, despite the fact that the buildings look more regular. And so, despite these mass timber structures looking so simple and looking like, Lego pieces all coming together, simply in these videos that we all see and how fast they go up, the planning that goes into them and the coordination, as you guys have seen in some of the other presentations today, is incredible, right? So much work from the design team, the construction team, to actually bring these structures to life and make sure that they are really coordinated properly. And so one of the big things we're seeing right now in the mass timber industry is how do we get to market faster? How do we design our buildings faster. Because if mass timber is going to continue to grow as a real construction type and as a new structural material, it has to be speedy. It has to be fast. It has to be able to compete in a time to market with either a steel or a concrete structure. And that's something where there's been a lot of struggles. A lot of the structures that we see so far are, either one-offs or demonstration projects. There's a lot of those where you have a lot of longer lead time to develop the design, make sure it's all thought through, planned through. But we start getting into the more, prototypical, whether it's spec office building or a multifamily development, you have to be faster to market. And so one of the things that we're looking at doing is developing, this computational platform, we call it Branch, which allows us to basically programmatically create these mass timber structures and programmatically do the structural design. And it doesn't take away from the fact that you still have to do all the coordination, you still got to do the mechanical systems and all that type of stuff, but it allows you to have a quicker iteration cycle through that type of stuff. And so with this Branch platform, which is built on top of Rhino, we're able to do all of our 3D, LOD 400, 450 fabrication modeling of the timber structure. We're also able to do our structural analysis. Then we take that through into generation of the shop drawings, automatic generation of the shop drawings of each of the timber pieces and the steel pieces. And then we take it through to the CAM files and the container planning and logistics. And these branch models have a link into Revit, because obviously, as we're in schematics or design development, we're not doing the full fabrication level of detail at that point, but we're able to kind of take the optimization that we're doing in the branch paradigm and bring that over into Revit for our structural documentation coordination with the architect's models. And so, like I said, here's this T3 Atlanta project going up, and it looks all very simple. But you've got hundreds of penetrations. You got so much coordination, despite the fact that it's really quite a simple structure. And so figuring out, the mechanical coordination and bringing that in and is obviously key. And so with this Branch platform, we're doing things like, for example, this is looking at the mass timber floor vibration, which is, a really big driver in the optimization of these mass timber office structures. Is what is your floor structure? How bouncy is it? And that actually tends to control the beam sizing and the panel sizing for your bays. And so this little video here is showing you basically a real-time response spectrum analysis. So we're able to kind of change bay sizes or look at different floor plates and understand how our response factors or our accelerations on the floor plate change as we look at different grids. And this Branch platform also allows us to do things like looking at logistics. So this is looking at, automatically packing your trucks, automatically sequencing your structure. So every color on this floor plate represents a different truckload of material. So we understand how the structure is coming together in 4 dimensions. And that's really what enables these mass timber structures to go together quickly on the job site. And then this idea of bringing the site installation feedback back to the structural engineers and back to the designers and the architects, so you have this, this guidance of letting the real building process impact your design. I think that's key to achieving efficient mass timber structures. And so, of course, once we start building these mass timber structures, the benefits are obvious. You've got the embodied carbon. You've also got just such a beautiful work environment. And so we're excited to see these structures, really proliferate across North America, and we're excited to see what the future is gonna bring. With a lot of these tools we've seen today already, there's so many people looking at what the next steps are for the digitalization of our mass timber industry, and I think it's really exciting to see. So with that, I'd like to close, and I guess I'll hand it back over to you, Thomas.
Well, I mean, amazing presentation as always. Your company is involved with just the most amazing projects around the world. I mean, it's really, really breathtaking. Lots of questions that I have. I mean, specifically around working in China. I mean, it's a totally different regulatory environment there. Yeah. You spent a lot of your career there. Do you think that these? I mean, you're really kind of pushing the edge, building these kind of Buckmeister Fuller domes and whatnot. Do you think that would happen in North America, or are they more open to kind of pushing the limit of engineering there? What's your opinion overall on that?
It's an interesting question. I would say I worked in London for several years in the UK, and I would say the London architects dared to dream bigger in China than they did in Europe. It was interesting, and it's not necessarily that the regulatory environment is perhaps a little bit less prescriptive, but in general much less educated than the Western regulatory environments, and in some ways much more challenging, particularly from a fire perspective, to get these timber structures through. The number of meetings I've had to sit through trying to convince Chinese building officials on the fire performance of timber is incredible. So I think we're starting to see it's really about the clients, and actually just before COVID happened, we were looking at a giant grid shell in the U.S. and just outside of Philadelphia, which would have been at a very similar scale, and so I think architects in the U.S. and in Canada are starting to dream bigger with timber. I think it's only a matter of time before we're going to start to see the same types of things here.
Yeah, and I mean, I don't really know this, but I mean, just looking at the use case of using wood in those type of high humidity environments, it just seems like they're kind of pushing the envelope on literally on the use of that type of material in that environment. Or is that, I mean, I don't know, is that good for wood to be in a high humidity environment like that? Does it affect the long-term durability? Was that part of the considerations that you had to work through?
Yeah, actually, I mean, wood as a structural material is actually really good in high humidity environments. In some ways, a lot better than steel. It's why you often see it in swimming pools, because it equilibrates with the surrounding environment and achieves its moisture content and equilibrium moisture content, and it's not a structural problem having wood in high humidity conditions. So that wasn't really an issue. Actually, our bigger concern was all the steel components. And making sure that you don't get moisture degradation or rusting over time of the steel components.
And I mean, you'd have to have a lot of considerations around, humidity levels during construction, and then after you get the enclosure and humidity comes up, and if you've got a cladding system over top of that, you potentially could have some shifting and whatnot.
Yeah, no, I mean, it's definitely something we had to consider, and the creep performance of timber can be impacted by the humidity level and the moisture content level of the wood. But it was something that we were able to get happy with from a timber engineering standpoint. We actually did a lot of testing on that particular subject, the moisture performance.
So your firm, I mean, just a little bit of background. You're based in Canada. You've got a team that is based in Canada, or you have teams all over the world that work on these projects?
Well, so we're based outside of Vancouver, but that's our headquarters and our main office. We've also got offices in Seattle. We've got some team in London and in Europe, and we've obviously got a partner company in China. But we've got a lot of installation crews working across the U.S. because we do a lot of work in the States, also in Canada. But I would say the North American market is certainly our main focus, and then with I guess the secondary focus on China.
And that branch, which seems to be like a plugin for Rhino, is that a commercially available product? Like, are you productizing that and making it available?
That's in the works. It's in the plan, but it's not yet publicly available. But I think the idea it's not just a plug into Rhino. It's actually a whole own object model, and it has instantiation into both Rhino, Tekla, Revit, etc. And so the idea is that it's kind of a holistic approach to analyzing and designing and creating a manufacturing platform for these mass timber structures. Yeah,
amazing. Simply amazing work. Thank you so much for sharing it. Fantastic visuals, and hopefully we can have you back maybe again in 12 months time.
Yeah,
but, thanks so much.
I mean, it's only a tribute to the architects and the clients who have these visions. I mean, we're there to try to make them happen, but I guess my encouragement to all the architects and owners out there is dream big, because it can be done with wood. It really can. And we're just fortunate and privileged to be able to work with architects who have such visions. It's really awesome and really neat to be part of.
Cool. Well, thank you so much, and we'll talk soon.
No problem. Okay. Thanks, Thomas.